right, so our last indeterminate forms that we have to deal with L'Hopital's rule are 1 to the infinity, 0 to the 0, and infinity to the 0. Remember, we kind of again thought of all of these as like battles between the values showing up. That infinity to the 0 is the infinity base making an infinity, is the 0 exponent making it 1. So we kind of have this issue with all of them. And then we'll just a reminder that 0 to the infinity is not indeterminate. So 0 to the infinity is usually 0, but if that infinity is negative, it could be infinity or negative infinity or does not exist. So if you are curious about why infinity 0 to the infinity is not an indeterminate form, I'm making another optional video about it that you are welcome to watch. I'll also talk in depth about 1 to the infinity and why 1 to the infinity is an indeterminate form, but why sometimes it's not. So anyway, I do recommend watching that video, though it will be optional, and hopefully it'll answer any of your curiosity questions. All right, so how do we deal with indeterminate forms like this? And the answer is we need to remember that natural log and e cancel each other out. So in other words, if I have e to the natural log of a function, then it just equals to that function, which means I can go both ways with this. If I have a function, I can write it as e to the natural log of that function. And that is what I'm going to do here. So it's actually going to be a little bit similar to what you guys did when you were learning logarithmic differentiation. So to understand, let's just jump into a problem. I'm going to look at the limit as x approaches 0 from the right of 1 plus sine of 4x to the power of cotangent x. So as usual, when we have a limit, the first thing that we want to do is plug in. So we're going to plug in 0. And 1 plus sine of 0, well, sine of 0 we know is just 0, so this is 1. And then cotangent, I'll just write a little plus there since that's 0 from the right. Cotangent of 0 from the right, we can think of as cosine of 0 from the right over sine of 0 from the right. And cosine of 0 is 1, and sine of 0 is 0. So while the sign of infinity is not important here, I could just say this is clearly 1 to maybe it's positive infinity, maybe it's negative infinity. The sign of infinity is not important here. It's really mostly important in our infinity minus infinity case. I'm still going to go and check. And I'm going to do that here by drawing a graph of sine. So if I'm looking at sine of 0 from the right here, then I'm looking at values that are on the right side of 0. And I can see that as I get closer and closer to 0 on the right side, those values are positive. So this is actually 1 over 0 from the right, which is positive infinity. So this is 1 to the power of positive infinity, which is an indeterminate form. So what we're going to do here is rewrite this thing as the limit as x approaches 0 from the right of e to the natural log of 1 plus sine of 4x to the power of cotangent x. There we go. Now, there are two things that we need to remember here. One of them is our third ln rule. We already saw the other two ln rules today. So our third ln rule is ln of a to the b is equal to b ln a. And that's going to be important for this right here because it means I can take this cotangent and move it to the front of my line. Now, the second is that I can move that limit inside of my e. So in other words, if I have the limit as x approaches some constant of e to a function, that's the same thing as e to the limit as x approaches a constant of that function. In other words, the limit doesn't it's not applying to the e, it's only applying to the function part. If you really want to think about this, let's say that I have the limit as x approaches 5 of e to the x. Where does that 5 go? It's not changing the e at all. This is just e to the 5, which is the same thing as e to the limit as x approaches 5 of x, right? So I can just move that limit to the inside. So that's what I'm going to do here. So we're going to have e to the limit as x goes to 0 from the right. Now I'm applying my log rule, cotangent x times natural log of 1 plus sine of 4x. Okay, now what? So now that e doesn't matter, I'm going to highlight it so I don't forget it. It's really easy to forget your e in these problems because we're going to go and we're going to bring that limit off to the side and just do the limit. So I'm looking at this, we're going to call it star. So we'll go down here and just do the limit as x approaches 0 from the right, cotangent x, natural log of 1 plus sine of 4x. Whew. Let's plug in. So we already plugged into that cotangent, and we saw that cotangent of 0 from the right was positive infinity. We also already plugged into 1 plus sine of 4x and got that that was 1. So this is times ln of 1. But ln of 1 is 0. So this gives me my infinity times 0 form. This thing has a trig function in it. And trig functions, I can easily move to the denominator. When I'm thinking about what's going to be easier for L'Hopital's rule, is going to be having 1 over cotangent, which is tangent, in the denominator, easier or harder than having 1 over ln of 1 plus sine of 4x. Clearly, that trig function is going to be the thing to move to the denominator. Cotangent x is just 1 over tangent x. So when you have just a trig function, that's going to always be the thing to move to the denominator. That will not always be true if you have not just a trig function. So if I had like cotangent x plus 1, then I wouldn't be able to apply my reciprocal identity. So if you can apply the reciprocal identities, move the trig function to the denominator. Actually, we'll do this with an asterisk. To the denominator when we have infinity times 0. Okay, so now when we plug in, we've already plugged into that ln. We got that that's ln 1, which is 0, and tangent of 0 is also just 0. So now we can apply L'Hopital's rule. So this is the limit, oops, as x approaches 0 from the right. Now be careful, this is going to be a chain rule here. It's actually a double chain rule. We have ln of 1 plus sine of 4x. So I'm going to put 1 plus sine of 4x on the bottom, and then the derivative of sine of 4x on top. So that's cosine of 4x times 4. That's my numerator. And then in my denominator, I'm going to have secant squared of x. So just to remind you of how we did the denominator, natural log of g prime is equal to g prime over g. So ln of 1 plus sine of 4x prime is 1 plus sine of 4x prime over 1 plus sine of 4x. Okay, now I could plug in. And if I plug in, I might get to an answer, but right now having it in this form is a little bit hard to look at with all of those fractions. I have this complex fraction, so I am going to just immediately simplify this to be the limit as x approaches 0 from the right. I'm going to keep my numerator there, cosine of 4x over 1 plus sine of 4x, and then secant squared, I'm going to move up to be cosine squared of x. So that right there is just to make it a little bit easier to plug in. When I plug in, what do I get? So here I'm going to get cosine of 0 is 1. Uh-oh, my screen froze. Hang on. Okay, so we are going to plug in here, and we're going to get, when I do that, 4 times cosine of 0 is 1. So that's 4 times 1 over 1 plus 0. And then cosine of 0 is 1. And this just gives me a 4. Be careful. This 4 is not your final answer. We want to remember to not forget to bring that e back. So our final answer here, this implies that the limit as x approaches 0 from the right of 1 plus sine of 4x to the power of cotangent x is equal to e to the power of 4. And that is my final answer. Okay, so these problems are a little bit long, so I'm going to go to another video to do the next one. That's all.